Okay, so today we will simulate in MATLAB the system we were discussing last time. And for the system, we discussed already the equation we need to obtain the initialization, the equilibrium point. In the equation that I got in the whiteboard, I made a typo. This is supposed to be the current IV, and this is supposed to be the current IQ. And something else that I realized when I was putting the equation in the whiteboard now is that I forgot to put the time constant. Okay, so we need to consider those things. So that's the first part of the initialization, in which we consider the machine in a steady state. So we use this very particular model just to get the initialization. So we get all the state variables and algebraic variables for a specific equilibrium point. From that point, we're going to consider at some time a short circuit that will move the system from the equilibrium point, and the fault will be clear, and the system should go back to the equilibrium point. And when we go back to the equilibrium point, then we need to use the dynamic model. The dynamic model now use a different circuit for the machine. It's not the circuit in a steady state, but for dynamic simulation. So we need to go back to that model. So last class, we have the 4 differential equation we need for this representation, and I just wrote the circuit. But from this circuit, we need to obtain the algebraic equation. So that's what we're going to discuss now. There. There. So here we have the model of the machine, and this is for dynamic simulation. When we clear the fault, then this is what we have to consider for the machine. And this will be related to the algebraic representation of the machine that will connect the algebraic variables, which in this case are the current in the stator in the machine, with the state variables in the machine. The state variables are going to be in this model the voltages EQ prime, EV prime, and the angle delta. So in this circuit, we have complex equation because we are assuming that this is very fast, reach a steady state immediately. That's why we use this model, a phasor circuit. This is the slack bus. The voltage is fixed, a phasor. But now what we need to obtain here are the algebraic relationship for our variables. So what we're going to do, we apply a Kirchhoff voltage law in the only loop we have here. And then we have this complex equation. Voltage V2 is 1 angle 0. So here I am just considering the magnitude because the angle is 0. So from this complex equation, what we can do, we can simplify the equation, because here you will have to multiply 3 complex quantities here, which might be tedious. So what we can do, we can multiply this equation by exponential of negative j delta. By doing that, exponential of negative j delta multiplied by this get canceled. As you can see here, that term disappears from there. And when we multiply exponential of negative j delta by this get canceled as well. And then you have these 2 terms. But this term now is multiplied by exponential of negative j delta. This is a complex equation. So we take the real part from this equation. The real part here will be EQ prime. We can put it on the other side of the equation and become negative EQ prime. And here we need to get the real part. The real part will come from the product of these 2 terms. You have negative j squared. So it's plus these reactants multiplied by IV plus B2 cosine of delta. cosine absorb the negative sign. So cosine of negative delta is equal to cosine of delta. So we have that there. Then we take the imaginary part. The imaginary part is negative EV prime. We send this to the other side, become positive EV prime. Here, the imaginary term become these reactants multiplied by IQ plus B2 sine of negative delta. So sine of negative delta is negative sine of delta. That's why we change the sign here. So from this circuit, then, we obtain these two algebraic equations that need to be added to the set of differential equations that we have. I made the correction here. So this is the correct current. And also, we are adding the time constant that I forgot to write last time, plus the two equations with the related to the motion of the machine. So what we need to solve these four differential equations, two algebraic equations simultaneously. Yeah. So this is what we're going to do today. I already put in Canvas some of the code that I worked on this problem, and you should have it. MATLAB code there. Were you able to download this? Do you have it? So we're going to create a function that finally we want to obtain the time and the state variables in time. And so far, this is what we worked last time. Come on. There. We have discussed how to obtain the equilibrium point. As David mentioned very well last class, we don't need a formal power flow set of equations because the system is so simple, and we can use the expression we know for the power flow between 2 points that use the voltage magnitude and sine of the angle because the system doesn't have losses. And all of these need to be divided by the equivalent reactants. So we discussed this expression, but there is the solution for theta 1, the angle at the terminal of the generator. What about now? Oh, okay, so do you have the code? Okay, perfect. So we have the calculation of the equilibrium point there. I said last time, then if we know the voltage, we know everything. So with the voltage already determined for this circuit, we can determine the current that flows through the line. How? By taking the difference of the voltages and dividing that by the impedance of the line. Okay. In this code also, I already stored the data. I mentioned several weeks ago that it's convenient to store the data in just one location. So when we make changes, those changes are applied to everything you use in your code. So the data is already at the bottom here, and I put everything that we need for this system. Yes?
A couple quick questions. Can you just briefly explain what the time constants mean in terms of the problem?
For this problem, this is the same discussion we had last class in regards to the why we're going to neglect or assume that some dynamics are really fast. All right, and that is by design. So the machines are going to design with 3 dampers. That's the assumption we're having. But those dampers are going to target different time after a disturbance. The first part is called the subtransient response. And that there, we're going to have a huge torque that will try to damp the machine, but it's going to happen over a few cycles. But then by design, we will have other damper with different physical characteristics that will respond in a longer time. So we will have a huge important action at the beginning, first cycle, and then we will have a more sustained action over several cycles after that. And And then also we will have some dynamics related to the field winding as well, right? So these time constants are related to the field winding dynamics and also to the 1Q dampers. You know? We're ignoring the 1D, 2D, and 2Q dampers. Those are going to be assumed very fast, and they are going to respond instantaneously. Okay? Any other question? Okay. All the data is there, and we have, let me close this one. We have so far the equilibrium point up to this point, okay? Not the equilibrium point. All that we did and we discussed last time is to obtain the power flow solution that in this case correspond to the line 6, in which we solve for the angle θ1. So when you obtain the voltages and the current, then we will need to use the steady state model of the machine. And we proceed with the 6 steps we discussed last class. So step 1, we are going to determine the angle. The angle of what? That complex voltage behind the quadrature reactance. And that corresponds to line 11 and 12. This is going to be the voltage in line 11, the voltage behind the quadrature reactance. And then for delta, we just take the angle of that complex quantity. When you have that angle, because we have an expression for the current, we solve for IQ and IV. When you have that, then we can determine EFD using the magnitude of the voltage behind the quadrature reactance. We know that this magnitude needs to be equal to EFD plus this voltage drop. So we solve for EFD and we get an initialization for EFD. I mentioned that EFD is going to be related to the actual DC voltage we apply to the field winding, right? So if we want to increase the terminal voltage in the machine, we need to come here and increase that EFD. Later, when we keep adding more details to our model, we will have an automatic voltage regulator that will automatically control EFD. At this point, we're going to assume that EFD is calculated here, but it's going to remain fixed. In the classical model, we did that already, right? We assume that the magnitude of that internal voltage in the classical model was fixed for the purpose of the simulation, right? The same thing we will do with EFD. But later, that's going to be a state variable that will be controlled by the AVR. So we have EFD, and then we go to the first differential equation here. If this is in a steady state, this is known. We have the current. We solve for EQ prime that will make this derivative equal to 0. So we solve for EQ prime, and the equation is in line 16. Same idea with the second differential equation. We set the derivative to 0, and we solve for ED prime, and that is line 17. In the following differential equation, this is easy. If this is 0, then the speed is 1 per unit, is synchronous speed. Okay. So after this power flow calculation, we apply the steady state model and we get the equilibrium point of the machine. That's what we did. So what we need to do now, we need to simulate. We need to consider a short circuit, and then we need to consider the simulation when the fault is clear. First of all, because we need to use this in the simulation, let's define the variables for our system. If, for lack of letters here, I show there on the other side of the whiteboard what is going to be our description, and we have used these letters for describing the model before. this is what we're going to consider.
As I didn't adjust the camera when I was explaining this in the whiteboard, I'm going to explain this again. Our system is modeled by a set of differential algebraic equations. So we have two vectors of nonlinear function, f and g. But to use a ODE solver in MATLAB, we have to specify just one vector of nonlinear functions. We're going to call that vector h, and we're going to include f for the differential equation and g for the algebraic equation. When we do this, also we will define the new vector of variables, x and y. So with this definition, how we're going to tell the ODE solver which one is a differential equation and which is an algebraic equation, we're going to do that by using the mass matrix M. And the mass matrix M is defined as described here in the equation. So with that, this is what MATLAB, the ODE solver in MATLAB will use. As you can see here in this equation, we can do the multiplication for the first block of this set of equation. And we're going to have I times x dot plus 0 times y dot. Of course, this term will be 0. The second block of this multiplication will be 0 times x dot and 0 times y dot. Of course, these two terms are 0, and we obtain exactly what we have originally in our representation, a set of differential and algebraic equations. You need to note that in the mass matrix, we're going to have a 1 in the diagonal, only for those diagonal terms that are related to a state variable. As an example here, I have a system with 2 state variables and 1 algebraic variable. So you have the differential equations and you have 1 algebraic equation. And as you can see here in the mass matrix, all the terms are 0, except for these 2 diagonal terms that are going to be related to the state variable x1 and a state variable x2.
This is related to EV prime. This is related to delta. This is related to omega. But for the algebraic equation, we need to pick something. It doesn't matter which equation is going to be related to its variable, but we need to pick one and keep that in all our code. So I put EQ prime first here. So I'm going to say that this equation is related to IQ and the other IV, okay? But I can pick any order, actually. These are algebraic equations. So when you go to that function, then we need to load all the variables, because for a given time t, we're going to have in Z, we're going to have all our variables. So, and we're going to load the variables in that order. So we're going to put here loading variables. So EQ prime is going to be the first component in the vector Z. EV prime, second component. Then we have delta. Then we have omega. And then the algebraic that we arbitrarily pick IQ first. And then IV. I'm going to move these so it's more organized. So we have the variables, we have the data, and now we can start writing the equation. The output of this equation, the result of this function h is going to be stored in out. So we're going to have 6 equations. 4, 5, 6. And we need to write down all the equation right here. So I can be more specific. This is going to be differential equation. Oops, not that one. And these are going to be algebraic equations. The first one. Here we have the set of differential and algebraic equations. And as I explained in the classroom, each of the state variables are going to be associated to their corresponding differential equation. So in this case, EQ prime is going to be associated with that equation. Then we have ED prime, delta, and omega. So when we look at the vector z that have, this vector has the variables of our system, z1 will correspond to EQ prime, z2 ED prime, z3 delta, and z4 omega. Then we have the set of algebraic equations. And at this part, it doesn't matter the order of the variables that we associate to each of these equations. But when we pick an order, we need to stick with that order. So in the classroom, I arbitrarily picked that for this fifth equation, we're going to associate the variable IQ. And for the last equation, we're going to associate to this equation the variable ID. So in the vector Z, we will have in the term, fifth term, we're going to have IQ. And in the sixth term, we're going to have ID. With this definition for the vector Z, then we completed our code. So we will have here, we will have from line 52 to line 57, the loading of the variables. And then from equation 50, line 59 to line 65, we use these variables in the data to fill all the differential and algebraic equations. So far, okay, we have the calculation of the power flow voltages. We have the initialization of the variables, state variables and algebraic variables, we're done. And we put the function of data and differential equation. So now, what about if we simulate the system from the equilibrium point? We should get flat response. No variables should move in time. So we can do that. But in this case, because we're using differential algebraic equation, we need to set what is the mass matrix for the system. And we will have to define that here. So we have 6 variables, so we can define immediately that is a matrix full of zeros. But the first 4 diagonal terms are going to be 1. So we can define that from 1 to 4 in the rows and 1 to 4 in the column. This is going to be equal to the identity of 4 by 4. So that's the mass matrix for this case. And then we will have to tell the solver that we're going to use a mass matrix called M. Yeah. Another parameter that I like to apply here that will affect the accuracy is the maximum time step we will pick. It can be 10 milliseconds. Okay. Invoking solver. Then you have T and Z, that's our combined variables. And this is going to be OD 15S. The function we're using for this is called H. And then we need to define the time for the simulation. It's not time zone, where that thing come from. Ah, darn it, there. Time, we can simulate for 10 seconds. So we have time, and we need the initial condition for Z0, and we're going to tell the solver we're using these properties for the solution. Okay. So what I forgot to do here, initial condition, we need to define, in this case, what is Z0. So all the variables are calculated already here. So all that I'm going to do here is to put them in order. So the first one is EQ prime, then EV prime, then delta, then omega, then IQ, and then IV. And with those numbers that we calculated, we should be in a steady state. So if we invoke this, then we can do the plotting. So we're going to open figure 1, and we're going to plot all the variables, T and Z. And that should be for now, and this is not going to be, we change the variables, this is Z. All right.
Can you scroll down to the invoking solver?
Okay. So if we run this, hopefully this works, and we should get a steady state solution. So T and Z, chapter 6, single machine, infinite bus. Okay, we're fine. That's what we expected. For plotting reasons, I would like to increase the line width so we can see this clearly. So by doing that, then the line should be thicker. Yeah. Okay, now we need to apply the disturbance. So what we're going to do, a short circuit. Where? At the terminal of the machine. What happened in that situation? This system is so simple. Still, what happened in the machine? The electrical power go to 0. So what do we need to do? We need to describe that situation. So what we're going to, the easiest thing to do, we copy this function. We're going to copy this function, and we're going to create the equation during the short circuit. So this function will not be the same. This is going to be H during the short circuit. And during the short circuit, everything is the same except the electrical torque here is going to be zero. So the machine speed up there. What happened with this variable now? We need to consider now that you have here a short circuit. If you have a short circuit, these reactants will not get involved with the current. And the same thing with the voltage. So in the equation, we need to get rid of the reactance of the line and voltage V2. So we're going to modify this. When you have a more complicated system, the same procedure needs to be applied. this algebraic equation will change as well during the short circuit. And we need to have a proper representation for that. Yeah? So those are the equations during the short circuit. Are we good? Did you make the changes?
So in the classroom, I indicated that the differential equation for the speed can be reduced to this term. And even though this is true, during the short circuit for this system, the electrical torque will be sent to 0. This is not something we have to do. Why? Because now we're using different algebraic equations. So when you have this short circuit, the condition of the short circuit are applied to the algebraic equation. So in this case, if we have a short circuit at bus 1, basically we're going to obtain a current that is purely reactive. So the current will be lying the voltage 90 degrees and the acted power will be 0. Therefore, the electrical torque will be 0. And by enforcing the short circuit condition in the algebraic equation, that automatically will define that the electrical torque will be 0. So the expression for the electrical torque, when we force this condition for the algebraic equation, should vanish in this case. So we have an expression that is EQ prime multiplied by IQ plus ID prime multiplied by ID plus some additional term given here, EQ prime minus XD prime, XQ prime minus XD prime multiplied by IQ, and ID. So for the short circuit, if we calculate all this expression, it should give us 0. So this part is not needed. We only need to enforce the short circuit condition in the algebraic equation. Therefore, the equation that we need are going to be given by line 81 for the derivative of the speed. We don't need to make the electrical torque equal to 0 because by modifying the equation now in line 83 and 84 to consider the short circuit, the electrical torque should be 0. So these is the set of equations we should consider for the short circuit condition.
So we have the initial condition, and here we're going to apply the short circuit. Short circuit. Short circuit. And we're going to simulate this for some clearing time. I think that I said 0.1 second. These need to be down here after the simulation parameters. And we're going to delete the time. There, the short circuit is a new time. And now we're going to invoke the solver, OD15S. We're going to use a different function now, which is H during the short circuit. We have a time from 0 to 0.1. Then we have the initial condition, which is the equilibrium point. And we're going to tell them that we need to use the options, a mass matrix, and a maximum time step of 10 milliseconds. And then we will get a solution. We will store these in T1, Z1. Then we're going to clear the fault after that time, 0.1 second. So To clear the fall, we need to have a new initial condition here. And the initial condition here is going to be the very last variables we have for the state and algebraic variable, that one. And the time for simulation is going to be from 0, 1 to 10 seconds. And then we're going to invoke the solver. We are using the time 2 and variable C2 for this part, OD15S. The function is just H. We have the new time, new initial condition, and the options. When we are done with this, we do the same thing that we did before. We're going to concatenate the result. So the time is going to be T1 and T2. We're going to put the time in order, of course, and then the variable is going to be C1 and C2. And then we will plot. You with me? Were you able to make these changes? And we simulate. Okay, so we have an improved model. We have the classical model before, but now we have the two-axis model. What we can do here, well, let's see, is it any different from the classical model? We can have a different figure here, figure 2, and we can plot this in the phase plane. But the phase plane, what is the dimension of the phase plane?
Several variables. It's gonna be
For the state variable.
not gonna be able to see it.
4 dimension, we cannot see it. So what we're going to plot? Well, we can see just one part of that space, which is going to be delta and omega, okay? So we plot delta, which is the third variable, but these are z, we call them z. And the speed here, and then that's the solution. Is it a little bit different than before? It look very different. What happened with the first part? We're supposed to move from the equilibrium point to the short circuit and then clear the fall. We need to check this a little bit, yeah?
Here I have a screenshot of the code. So at the beginning, we calculated the state and algebraic variables during the short circuit, and then we did it after the short circuit, and we concatenate the result. So T and C should have the result we needed. But then in line 88, I was overriding everything again. So this line remained from the previous work we were doing. So basically the mistake we had was we forgot to delete these lines. Now there is a very interesting question about damping. So in the classical model, we have an equation for the speed in which we assume that the torque in per unit is about the same than the power in per unit. So the equation in the classical model was mechanical power minus electrical power. But here we intentionally included a term which was KD multiplied by omega minus 1 to represent somehow damping. Well, in the two-axis model, this is not needed anymore because the damping is going to be included through the WineQ damper. Here is a very interesting question from the student.
So the reason we have damping, even though we didn't put a damping parameter, is because of the time constants?
Because of the dampers. The equation that we have right here.
The time constants account for the dampers in this model.
Right. These are a model for the damper 1Q. So the currents that will appear through the damper will be related to damping torques that will make the machine to reduce the oscillation.
IQ and
That's the IQ and AV are the current in the stators, but this These variables here, one is related to the field winding and the other with the 1Q damper. Okay, so the two combined will describe better the damping. Very good observation. Before we have to have this mathematical representation, which is not realistic, but here you model the damper completely. Okay, so what we're going to do next Monday, please take a look at the code. There is something strange. Maybe everything is fine, but we need to check this. What is strange for me? We have here the speed. Here we have the angle. It seems that the system is stable, but the system started from the equilibrium point, and the system should go back to the equilibrium point. But these are not connected. There is something strange. So I need to check what we wrote and make sure that we have the right equation. Yeah, this is kind of off, but we will check. On Monday, we will use the code and we will run some simulation. For example, what simulation, which is related to the homework, the critical clearing time. So we will run a code how we can do that. And then quickly, we need to simulate the two-machine system within Infinite Blast and see what kind of behavior we get in that case. Okay? Thank you, guys.